Hi everyone, back for part two. Last lesson we looked at what the index refraction meant and how it was simply the ratio of the speed of light in vacuum, 3 times 10 to the 8th meters per second, divided by the speed in a material. And because the light speed always decreases in a material, the index of refraction was always larger or equal to 1. But we didn't discuss how we knew what these index of refractions actually were. Well, this lesson we're going to discuss how we measure these index of refractions using Snell's law. But first, let's do a little review of what happens when a light wave strikes a boundary between two materials. Well, before we start working with index of refraction, we've been just talking about light coming straight along the normal line. What happens if the light doesn't come straight along the normal line? What happens if it's hitting the boundary at an angle? So here I have air and a light ray striking the boundary at an angle. Now remember, just like we did with reflection, if I'm going to work with this light, I'm going to need a normal line. Oh, first I note that the velocity in the air is c and the velocity in the glass is less than c. So I put a normal line where the light strikes the boundary. Now notice now my normal line needs to go through the boundary because I'm going to be working with this light on both sides. Well, remember, a ray really just represents how these wave fronts are moving. So the ray is just a mathematical trick we work with. It really represents how these wave fronts are traveling towards the boundary. But as these wave fronts towards the boundary, this entire wave front is not going to hit all at once. What you see here is this part of the wave goes into the glass and immediately slows down. But on the other side of the ray, that part of the wavefront hasn't entered the glass yet. It's still in air, so it's still moving fast. So what ends up happening is this, as one side of the wave slows compared to the other side of the wave, the entire wave ends up pivoting. And what happens is the direction of the light that the light travels is going to change. And it gets bent inwards towards this normal line. So again, here are the wave fronts traveling through the air. When they strike the boundary, only a portion of the wave hits the boundary first. So part of the wave becomes slow, the other part of the wave front is still traveling fast. That ends up causing the entire wave to pivot and change direction. And then the wave fronts are moving at a slower speed inside the glass. This bent ray is called a refracted ray. The refracted ray represents how the direction of the light changes. Now again, physically what's happening is the wave fronts are changing direction because their speed has changed as they cross into the boundary. But it results in the ray changing direction. So as we work with these ray diagrams, remember they represent how the wave is traveling, and the wave's direction has changed because of the speed change. Now this only occurs when you hit at an angle. When you came straight along the normal line as we started the discussion, the entire wave hits the glass at the same time and the speed changes all at once. So this bending doesn't occur. But if I hit at an angle, part of the wave will hit the boundary first and slow first, causing the wave to change direction. So when light is slowed by material, the ray bends inwards towards the normal line. Now you can imagine what would happen if I ran this experiment in the opposite direction. If I started in the glass and went into the air, as the light hit the air, it would speed up first. And so the part that's going into the air would be fast. The part that's in the glass would still be slow. And then I would end up bending away from the normal line. So, in summary, when light enters a slow material, like going from air into glass or air into water or air into any material, since air is the light is traveling the fastest it can, then the light ray will bend inwards towards that normal line. But if you reverse the process, if light goes from a slow material like water or air, like water or glass, and travels into air, say, then the speed of light will increase and the light ray will bend out away from the normal line. If you come straight along the normal line, then the entire wave changes speed all at once, and then you don't bend at all. So you only see this bending of light, this refraction of light, when you strike a boundary at an angle. Now, that means that refraction, light going from one material into another, changes the way we see the world. Now, consider this example. Let's say you're standing on shore and you're looking at a fish below the water. Well, in order for you to see that fish, light has to bounce off the fish and make it into your eye. But first, the light is going to have to bounce off the fish and strike the surface of the water. Well, as that light strikes the surface of the water, it's going to be moving from one material, water, into another material, air. So I'm going to need a normal line there as a reference. Now, before I consider what's happening to light, I need to think about these materials. In the water, my index of refraction is 1.33. But in the air, my index of refraction is 1. That means that the bigger the index of refraction, the slower the light is moving. So that means in this situation, my light is starting in water, which is a slow material. And then it's moving into air, which is a fast material. So the light is going from slow to fast. That means I expect the light ray to bend away from this normal line. And it does. So on the way to my eye, the light is bent away from the normal line. It has changed the initial direction that it came when it first was reflected off the fish. Well, I have no way of knowing what the light is doing below the waterline. All I know is which direction the light seems to be coming into my eye. So to my eyes, I'm where I see the fish depends on where this light seems to be coming from. So if I project it backwards, I'm going to see the fish further back than it actually is. Now, this is why it is so difficult to grab something from underwater if you're standing above the water. As you reach into the water, the object is not really where you think it is. In this case, the fish is actually closer than where it appears to be. So, because of this refraction effect, the object seems to be in a different location. So next time you're swimming in a stream or a lake or somebody's pool, go ahead, place a shiny object like a quarter underneath the water, and then just try to stand back and try to reach for it. You'll see that it's not exactly where you think it is. Now, this effect of the light bending as it goes from one material to another, and the speed of light changing speed, this is the explanation for why dispersion happens. Now, you might remember back when we first started talking about light and color, we talked about dispersion as when white light is split into its component colors. But we didn't explain why that split was occurring. So here I have a prism, and I have white light coming into the prism. Now, this white light is really a mixture of all the colors of the visible spectrum, Roy G. Biv. And as it enters the prism, it comes out split up into its component rays. And we didn't discuss why. Well, if you look at the index of refraction for each one of these rays, you will see that it's slightly different based on the wavelength of the ray. That is, for this prism, if I looked at the index of refraction, say, for red light, it would have an index of refraction of 1.509. That's really close to 1.5, but it's a little bit larger. If I then compare it to measure the index of refraction for yellow light, I would see that it's also close to 1.5, but it's 1.511. So basically, it has a slightly larger index of refraction than the red light does. Because it has a slightly larger index of refraction, the light slows down just a little bit more, and the yellow light will bend a little bit more than the red light. If I continue on and look at violet light, I will see that it has an index of refraction of 1.521. Again, very close to 1.5, but larger than both red and yellow, so violet light will slow down the glass more than those colors. That means the violet light will bend slightly more, and the end effect is these rays will separate out as they go through the glass. So the index of refraction is slightly larger for violet than red, so the violet will end up bending more coming out of the prism than red light does. Next week we'll discuss how this also leads to rainbows with water drops, but that's next week. So consider this multiple boundary problem. I have light going from air into glass into water. This is basically you looking through the walls of an aquarium or a fish tank. So I start with an incident light ray traveling from air to the glass. And in order to work with it, I'm going to need a normal line. And I can measure the angle of incidence in the air, where I'm just going to label that theta A. It's starting here, so that's what the I stands for, incidence. But it quickly can become confusing. Are you talking about what material that light is actually the angle is being measured in? So by putting A on my angle measurement, that indicates to me that this is the angle when the light is in the air. Well, it's going from air, which has an index of 1, to glass with an index of 1.5. That means I'm going from a fast material into a slow material. That means this light ray should bend inwards towards the normal line. And I can measure this angle in the glass. Again, this is the refractive angle, but I'm going to call it theta G so I can keep track that this is the angle when the light is inside the glass. Well, after it hits the glass, it's on its way into the water. So here is another boundary, which means I can draw another normal line. But now it's going from glass into water. That is, it's going from an index of 1.5 to 1.33. So the glass has a slower speed of light than the water. So since this light ray is now speeding up as it goes into the water, it should bend away from the normal line. Now notice, if this was a window and not an aquarium, if I was going back in the air, this angle here would exactly match that angle there, and the light ray would come out at the same angle that it went in. But here we're going from air to glass to water, so we have 3 different angles. The question is, what about this angle of incidence here? So here's the angle of refraction going from air to glass. What about the angle of incidence going from glass to water? Well, this is where remembering a little geometry comes in handy. These normal lines are parallel, which means these are alternate interior angles, which means this angle here must be the same as that angle there. And so the angle of refraction from air to glass becomes the angle of incidence going from glass into water. Now, that's why you don't want to dive into the equations right away. You always want to draw a little bit of a diagram and get your angles in the right place and understand what you expect the angles to do. Are they getting larger going into the next material or smaller based on whether the speed of light is speeding up or slowing down? Now, the relationship between these angles and the index of refractions is described by Snell's law. Now, Willibord Snell was an astronomer, lived from 1580 to 1626. And as an astronomer, he was very interested in the behavior of light as it traveled through glass lenses. So Snell's law is what we call an empirical law. That is, he didn't derive it from first principles, he derived it from observations. And through multiple observations, Snell realized that light rays always obeyed the same relationship. And that relationship is this. If you take the incident material, that's where the light is starting from, take the index of refraction in that material and multiply by the sine of the incident angle, that's the angle in the beginning material measured to that normal line, it will always be equal to the index of refraction in the second material, the refracting material, times sine of the angle the light ray makes measured to the normal in that material. So Ni sine theta I equals Nr sine theta R. It's a very simple relationship and a very powerful tool, because although it's hard for me to predict what an index of refraction will be, it is easy for me to see how my light rays are bending and measuring those angles. So by measuring the angles of incidence and refraction, you can actually determine what the index of refraction is using this law. So let's take a look at a couple examples. All right, so here's first example. I have a light ray traveling from air into an unknown material X. The light ray strikes the material at an angle of incidence of 25 degrees and refracts at an angle of 14.5. What is the index of refraction of material X? All right, I can't stress how important it is to make a quick sketch of your problems when you're working on these problems. If you're going to make a mistake, it's going to be associating the angles and indexes and getting them mixed up by not getting them correct. So here I'm traveling from air into material X. So I know in air, I know in air, my n equals 1. And here I do not know what the index is in material X. I do know that this angle from the incident angle is 25 degrees. And I know the angle on the refractive side is 14.5 degrees. All right, notice that, and this diagram makes sense because air is the fastest material. So I know nothing, the speed of light can't be any faster than what is in air. So if I travel in the material X, the speed of light must decrease, must slow down, and therefore my light ray must bend inwards, and this angle must be less than 25, and it is. So I'm going to set up Snell's law to find out what this index is. So I start by writing down Snell's law. Ni sine theta I equals Nr sine theta R. Now, I stands for incidence, R stands for refractive. Now, again, to make it a little bit easier, I like changing the I's and the R's to subscripts that match the materials. So that is n in the air times sine of the angle in the air is going to be equal to n in material X times sine of the angle in material X. Well, that's what I'm looking for. And I know what these angles are. And I know that the index of refraction in air is 1. So I only have one unknown. So I just need to solve for this index, n. So nx is going to be equal to n in the air, sine the angle in the air, divided by sine the angle in material X. So now I can just put in my numbers. N in the air is 1. The angle in the air was 25 degrees. And I'm dividing by sine of the angle in material X. That's a sine of 14.5 degrees. If I calculate what this index is, this index works out to be 1.69. And there you go. Now, a couple of things to note. First off, look at my index. Remember, this always has to be a number greater or equal to 1. And so 1.69 means this is an index greater than 1. The speed of light is less than 3 times 10. This indicates the speed of light is less than 3 times 10 to the 8th. So that makes sense. Now, if you end up with an answer that doesn't make sense, 2 possibilities. 1, you might have mixed up the angles. That is, you might have put the 14.5 degrees with the air and the 25 in material X. That's one of the reasons why I changed my subscripts to help keep that from happening. The other thing that could happen is I gave you these angles in degrees. It could be that your calculator is in radian mode. So if you're getting an index that doesn't make sense, which for us means an index of refraction that is less than 1, then you want to go back and check that you put the angles in the right place and that your calculator is in the right mode. Okay? All right, let's look at another example. All right, a light ray travels from water into air, and the light ray strikes the surface of the water at an incident angle of 35 degrees. What is the angle of the ray in the air? Now again, I'm going to, before I dive into using the equations, I'm going to make a sketch and make note of what I know should happen. In the water, my index of refraction is equal to 1.33. In the air, my index is going to be equal to 1. That means in the water, I'm going from a slow material into the air, which will be a fast material. That means that this light ray should bend away from the normal line. And I expect this angle, the angle in the air, to be larger than this angle. Now they tell me that this angle in the water is 35 degrees. So regardless of how my math works out, I should get an angle in the air greater than 35 degrees. If I get an angle where this angle is less than 35 and the light bends in, that doesn't make sense according to these index of refractions, and that will give me an indication that the math is wrong. So let's set up Snell's law again. So my incident material is water. So rather than using I's and R's for incident and refraction, I'm going to use W for water. So the index of the water times sine of the angle in the water is going to be equal to the index in the air times sine the angle in the air. All right, well, I know the index in the water. I know the angle in the water. I know the index in air. I don't know this angle. It's in a sine function, which bothers me a little bit, but I'll just let it be. So this is what I want. So let's get that by itself first. I'm going to divide this index of the air over. So I have sine the angle in the air is equal to the index of the water times sine the angle in the water divided by n air. Well, I want this angle. I'm going to have to do an inverse trig function, but before I do it, I'm going to put the numbers in here and get what sine of the angle equals. So sine of the angle in the air is going to be equal to, well, the index of water is 1.33 times sine of 35 degrees, because that's the angle in the water. And I'm going to be dividing this by 1, because that's what the index of the air is. Now notice this could be water and glass, and then I would have different values for my n's. That's why it's always good to keep the n's till the last minute, because then you can put in whatever you need to. But if I put in these numbers, what I'm going to find is 1.33 times the sine of 35 is going to be equal to 0.76286. All right, again, a math check. I know the sine of an angle should always be smaller than 1. I should be between 0 and 1, and it is. And so that's a good sign. So now, this is the sine of the angle, though. This isn't the angle. So I'm going to need to do an inverse trig function to find out what the angle is. So the angle is going to be equal to inverse sine of 0.76286. Now, again, when you do an inverse sine like this, the answer will be in whatever mode your calculator is in. So I'm giving you degrees, so I expect an answer in degrees. So if your calculator is set to radian mode, you would get an answer in radians. So if your answer doesn't make sense, if I end up getting an angle that's smaller than 35, check the mode of your calculator and make sure it's set to degrees. But when you do this math, you get that the angle in the air works out to be 49.7 degrees, which is in fact larger than 35 as we expected it to be. So that's a good indication that the math is correct. So the problems aren't that bad. Again, the most likely part to make a mistake is mixing up your index and angles, putting the 35 with the air, or getting your index on the wrong place of the math equation. But once you have them set up, once you get used to these are pretty straightforward. So a couple of things to note. We're going to continue on with refraction next week. But notice that as I increase this angle on the incident side, if I go into a fast material, this light ray will continue bending further and further away from the normal. Now, that can only bend so far. Eventually, this light ray will bend over 90 degrees. And the question is, what happens after that? But that question is for next week. All right, you know about the chats online, Monday, Wednesday, Friday. You can email me questions. You can email me pictures of your work. This week's assignment is also set up fairly half and half with conceptual questions as well as mathematical ones. I don't anticipate you having much difficulty on it. But again, start early to give yourself time to ask questions as you do the work. All right, see you next time.